I'm Thomas Trinkle again. I'm going to explain this picture while I'm here because it'll take a while to get back to. So we're using calcium uh, ceramic and a PCl solution. So you take your PCl solution with a 10% weight volume ratio of chloroform, and you put your ceramic scaffolds in it, and you put it in a vacuum chamber, and then you use a centrifuge 3 different times to ensure that you get a proper mixing. And then they produce their ceramic polymer composite scaffolds. So the name of my paper, a new method of fabricating robust freeform 3D ceramic scaffolds for bone tissue regeneration. It was written by these guys. It was published in the Biotechnology and Bioengineering. So I was really enthused to read it when I saw that. So the scope was to establish a fabrication process for ceramic scaffolds to enhance mechanical properties and biological activity. And they wanted to understand what the addition of PCl would do as far as cell proliferation and mechanical properties. So as I said before, they used a ceramic powder and PCl. They made parts that were only the ceramic powder, and they put a photo initiator in there to center the parts. And then they made parts with 20% weight volume with PCl. They used the cell counter kit 8 and the universal tensile testing machine. And then they also used a standing electron microscope just to take these pictures, but it didn't really have any effect on the scope of the study. They just wanted to show what it looked like in the part. So the first is, how does the addition of PCl affect cell proliferation? So they did a 7-day trial, and they actually talked about a 14-day trial, but they didn't put it on their graph. The gray here is with the polymer, so you would think there's a pretty decent margin here, but they said the margin really didn't matter, that what they had for the ceramic polymer was good enough for what they needed. And then they also concluded that after 14 days, they still had cell proliferation into the scaffold, so they felt it was a pretty viable method for this application. The second is, how does the addition of PCl and the ceramic powder affect mechanical properties? And as you can see, with PCl, the compressive strength increases significantly. The reason that they only looked at compressive strength and not tensile strength is because they said the human body pretty much only deals with compressive strength, so there was no need to look at tensile strength. And this is more of a visual of what we got. So I do beat Trevor and Jordan with almost 5 megapascals, and still pretty low. And these parts were centered at between 1300 and 1400 degrees Celsius. And the parts, just so you understand, we got a volume of 4.5 by 4.5 by 1.8 millimeters. And then they said that since they're using micro stereolithography, the largest that they could produce in surface area was 11 by 9 millimeters. So we're looking at really small, but we're also looking at really, really small compressive strength. But they concluded the addition of PCl into the ceramic powder significantly affected your compressive strength and your toughness. So it was a good thing to add into the ceramic powder. So cell proliferation lasted over 7 days, which they thought was good, is what you want when you're putting it into somebody as a the addition of PCl does not significantly affect cell proliferation, even though it kind of looks like it does with the chart. Like I said, it didn't really matter. The addition of PCl significantly increases your mechanical properties. And so they concluded at the end that the addition of PCl is very beneficial when adding it to the ceramic powder. So when they were talking about mechanical properties, they stated that as the sintering temperature increased, your compressive strength increased, but then they referenced a graph that wasn't in the paper, so I don't really know how they concluded that. Maybe they just accidentally left it off. They test. Could they might have just gone with what they calculated on SolidWorks or something. So they tested a lot of things. There were a lot of key conclusions that I didn't address in this paper. They talked about density and shrinkage as regards to what your sintering temperature was, but the paragraphs were real small. Didn't really get a lot of information on them. The two that I concluded were the most information that they had, so it's kind of hard to go through. But the research at the very beginning of the paper, it was really well laid out, so you knew exactly what they were going to do and how they were going to do it. And they did it really well. They just didn't conclude so great.
All right, my name is Jake Weigel. I'll be looking at more of the an application of hydroxyapatite that we've been discussing in the previous presentations. And in this study, it's not necessarily a study, it was more of a research paper. And then they didn't actually do any testing or build any parts. They just read a lot of papers and then kind of reported on. As we'll see, the contribution of the rheology, which is the study of the flow of a material, and how that affects the design process for these biomaterials for bone replacement. So that's the scope. And then is the analysis of these properties a worthwhile consideration is really the question that they're trying to address. So the material they used was hydroxyapatite just because it's kind of the most common for this application for bone replacement. So they just stuck with that when they did the research. Looked at 4 different process versions of it. First being injectable bone replacement, and you can see them all in the figure here. So that's typically injected with a syringe. Composite gel scaffolds, porous scaffolds, and then finally rapid prototype scaffolds, which was a really minor part of the paper actually. And the characterization tools, looking at storage and loss modulus, and then viscosity, which are kind of 3 of the primary rheological characteristics that they felt like exploring. All right, so for the HAP cements, which are the injectable, as you saw in the previous slide, these typically go in a syringe. The flowable materials can be injected into the irregularly shaped defects in the bone. So if you were in an accident or something, you wouldn't have a normally shaped defect. It would need to be something really custom designed for that to proliferate that bone growth. So with a flowable material, you can inject it in, and then as you saw in this first picture actually, they take that syringe, put it into that hole, and then as it sits there, it hardens and promotes bone growth, and eventually it degrades and natural bone will replace it. And so they use a thixotropic material to do this, which is flowable when you're applying pressure to it, and it's got a high shear, a constant shear on it. But then as it sets, the viscosity increases, so it becomes more of a solid. The issue they discovered with this in the research was that when people design these, they don't necessarily consider that when you put this material in a syringe, the liquid will flow faster than the solid. So as you're injecting it, the lower pressure at the needle, all the liquid will collect there, and that will inject first. And then left closer to the plunger will be just like a wet powder, basically. So you get to the end, and maybe that powder won't flow through the needle, and you've not accomplished what you want it to. So they just addressed that as a potential issue for the development of these materials. For the HAP composites, the viscoelastic moduli increase with HAP content, and then they decrease with increasing temperature. And they just kind of addressed a few different examples. They didn't, like I said, they didn't actually do any testing. So these figures here are kind of just like a generic overview of what you could expect, and the actual significance of these percentages wasn't really addressed because that's not the study that they did. They just pulled that from one of their other articles. They did determine that the rheological properties were important, so the gelation time, degree of cross-linking, glass transition temperature, homogeneity were critical to this hydrogel performance. But they did mention that with these hydrogels, they were really ineffective without the HAP phase in terms of their mechanical properties. So they um, quoted that as a necessity for them to have any application at all. They're also determined to be thermoreversible. So as I discussed in that last one, is kind of along the same lines where it's going to be a solution at room temperature when you're wanting to inject it, and then as it increases in temperature, it gets more of a gel-like phase to it. All right, and then we're looking at the rheological properties effect on porous scaffolds. And there are 4 different methods, well, 3 that I'm examining here, of accomplishing this. Freeze casting, where they did determine, like, this is a really generic explanation as to why that these things were the case, but the rheological properties played a decisive role in the pore size, porosity, and compressive strength, which, as we've addressed, for a bone substitute material, you need to have high mechanical strength in the compressive direction, and you also need to have a porous material that's going to incite new bone growth. Direct foaming was the next process they examined, where proteins are combined in the HAP suspension, and they attach to the surface of the present particles, and they form bubbles between them, getting that porosity. And then finally, the rapid prototyping component of this paper was, a half a page maybe. They addressed that it allows precise control of the pore size and eliminates the need for machining, and they accomplished all these parts using an inkjet binder printing method on a ceramic powder bed. Like I said, they didn't really address it, but they did mention it as being one of the best options going forward because it gives you the most precise control over the parts you're making. So in summary, dispersion based on ceramic nanoparticles shows complex rheological behavior, not solely based on the polymer matrix. So the addition of the ceramic particles and proteins to the polymer matrix needs to be addressed when developing new materials. It's not something that can be overlooked because in the research it has made a significant impact. Some injectable gels can show that thermoreversible rheological behavior, so that also needs to be considered. So when they're liquid at room temperature and then they change at body temperature. And additionally, the rheological behavior and mechanical properties of ceramic suspensions can be increased through the use of fibers. And that's just kind of a blanket statement they made at the end, just kind of in summary of all their research that they've done. Personal critique, a lot of new background research. I mean, they said that plainly at the front that they looked for only things that were 2010 and newer to make sure that it was relevant going forward. The figures, however, were not really that useful because they didn't really address why they were there. They just kind of threw it in, and you had to figure it out. And you could go look at the previous research paper that it came from if you really want to understand it, but there was really no explanation as to why they were included. And there wasn't any testing to include, so it's not typical for these presentations, at least, to have to report this kind of information, but these are the results they came back with. So